doubt is there. So good morning to engineering thermodynamics. Today we are going to see how to plot TS diagram, what are the different properties and lines which are drawn on TS diagram, as well as we will see one numerical to find out the enthalpy and entropy by using a steam table. So this is our today's content. So let's start today's session. So in a previous video, we already saw that how to draw PV diagrams, correct? So in PV diagrams, we are actually plotting the various point of saturated points, saturated solid, saturated liquid, saturated vapors, and accordingly we get one PV graph. Now in a TS diagram, suppose this is a vertical axis along which temperature is given, and this is a horizontal axis along which entropy is given. So remember, in our topic there are three kind of graphs. So PV graph, TS graph and HS graph. So this is a TS graph. In this, the graph shape we obtain is a bell shape. So we always obtain such kind of shape. Not exactly symmetry, but such kind of bell shape. And this curve is belong to saturated liquid curve. So all the points on this side, this curve is saturated liquid point, and this side is belongs to saturated vapor point. So vapor curve. So all these points belongs to saturation condition, and where these two curves get meet, and we observe the highest pressure and temperature where liquid and vapors are in equilibrium condition, that is called as critical point. So this is a TS representation. Now suppose there is any constant temperature process. So constant temperature process, so we come to know that the line will be exact horizontal. So any constant temperature process, so process line will be like this. T is constant. So temperature wise there is no variation. So constant temperature process. If any process is adiabatic process, so entropy remains same. In that case, we can say that the exact vertical line where entropy is constant. So if we are plotting any constant temperature process, then it must be visible as a horizontal line. If it is a constant entropy process, then it will be visible as vertical line. Next, pressure line. So pressure line, here suppose this is a pressure line. Constant pressure line, so P is constant. But when we supply heat, so addition of heat will first start rising its temperature. So we observe that the temperature at this point, then next, up to the saturation liquid line, it is continuously increasing. So temperature is rises. Then it becomes exact horizontal. And after this saturation vapor line, it again inclines. So this is constant pressure line. we know that at this point the property of our substance, pure substance, is saturated liquid. At this point the property of our pure substance is saturated vapor. And from this to this, saturated liquid to saturated vapor, there is a conversion, there is a phase change from liquid to vapor. This point, substance is completely in liquid form. At this point, substance, pure substance, is completely in vapor form. And from this to this, there is a phase change taking place. And we know that whenever there is a phase change, temperature remains same. There is no any rise or drop of temperature during phase change because we are supplying latent heat. Latent heat is responsible for change in phase, not for rising or drop in temperature. So we observe that during the phase change, liquid to vapor, the temperature remains constant. After vapor condition, if we are supplying heat, so it will be a sensible heat. Again, we observe there is a rise in temperature. So this is constant pressure line. Next is constant enthalpy lines. So constant enthalpy lines look like a curvical line. Such kind of lines are there, and these are the constant enthalpy. So enthalpy is constant. And last curve, that is for constant volume. Constant volume in this bell shape, it is curvical, little bit curved line. And as soon as it is move out from the saturation point, so it will be straight. Not exactly parallel to this pressure line, but it is straight. But within this dome, this constant volume lines are curvical, so volume is constant. So basically these kind of lines are there on TS diagram. So this curve, saturation liquid, this side saturation vapor curve, where both curve meet, that is a critical point. Again I am saying critical point is the highest pressure and temperature where we observe the liquid and vapor in equilibrium condition. When there is any process at a constant temperature, we observe that horizontal line. Any process at constant entropy, that is adiabatic process, then it is vertical line. Constant pressure, so outside the dome, we observe there is a rise in temperature. Pressure is constant, but rise in temperature due to addition of sensible heat. When it reach to this saturated liquid curve, then after whatever be the heat added is a latent heat, so we observe a phase change, and phase change takes place at constant temperature. Pressure is already set, so constant pressure, constant temperature, phase change is observed until complete substance converted into vapor. After that again we observe rising pressure, rising temperature. So this is pressure line. Little bit curve lines from left to right, that is constant enthalpy lines, and constant volume lines. So we observe inside the dome it is little bit curve, and outside the dome it is again become straight line. So all these lines are there when we observe a TS diagram. Now in this, we know that at this point your substance is in pure liquid At this point, it is in your vapor, saturated vapor. There is no any liquid part. Here, saturated liquid, there is no any vapor part. During this to this, there is a phase change, and phase change will not take place instantly. So at the beginning, some portion of liquid, saturated liquid get vaporized. Remaining part still it is a liquid form. Then onward heat supply, lateral heat supply, some more portion of liquid get converted into vapor. Remaining portion is liquid. Likewise, from this to this, there is always a mixture of liquid and vapor. So that is called wet vapor. So this zone is a wet vapor. This is saturated liquid, this is saturated vapor. In between these, it is a wet vapor. Now the wet vapor having some portion of vapors and remaining portion is liquid. So we must know how much wetness is there, or you can say how much vapor portion is there, and that is identified by an index known as a dryness fraction. And dryness fraction will started these lines. So these are the constant dryness fraction line. So here there is no vapor, so dryness fraction x is 0. Here everything, that complete substance converted into vapor, there is no liquid point, so it is x is equals to 1. So your dryness fraction line always lies between 0 to 1. So this might be x is equals to 0.2, this is x is equals to 0.4, x is equals to 0.6, x is equals to suppose 8, x is equals to suppose 0.9, then x is equals to 1. So these are the constant dryness fraction line. Now the most important part, the properties. To make it more simplified, I will erase the other unnecessary lines. Hopefully you come to know the various lines drawn or available on the TS diagram. This is the critical point. So I will erase the other unnecessary lines. We will draw again. So this is the TS diagram for suppose water. Water is considered as a pure substance. So TS diagram, we observe such kind of dome shape where this belongs to saturated liquid line, liquid curve. This belongs to saturated vapor curve. And this is our critical point. Correct? Now suppose we are considering a phase change take place at any particular pressure. Suppose we are considering a pure substance as a water. So anyone can reply, what is the boiling temperature of water? What is the boiling temperature of water?
100 degrees Celsius.
100 degrees Celsius.
Just a minute. Okay, now reply. Yes, boiling temperature of water 100 degrees centigrade, correct? But this boiling temperature of water 100 degrees centigrade, it is not absolutely correct answer. Why? Because boiling temperature point changes as per the pressure. No doubt, this 100, if I am drawing any pressure line, suppose this is the pressure line. At this point, it is pure liquid, that means water is there. When we are supplying a latent heat, this water start vaporizing, and at this point, complete water get vaporized into vapor, steam. Then after again, there will be a rise in temperature. So what is the temperature here? So from this point to this point, phase change takes place. That's when boiling takes place, where liquid part get vaporized. So what is this temperature? We are saying temperature 100 degrees centigrade. Correct? For water. So phase change takes place at 100 degrees centigrade for water. But this is true when we are considering pressure is 1 atmosphere. So we have to supply heat for conversion of complete liquid, complete water into steam from this point to this. So this much amount of heat is required to convert water into steam at 1 atmospheric pressure, and the temperature belongs to that is 100 degrees centigrade. Now imagine, suppose I am increasing the temperature, I am increasing the pressure. Suppose next time I want to boil the water at suppose 2 atmospheric pressure. So no doubt 2 atmospheric pressure line will be higher side. So suppose this is the 2 atmospheric pressure line. So first it will reach to saturation curve, then phase change take place. So horizontal line, constant temperature line, and then again sensible heat is added. So this is P is equals to 2 atmosphere. Now when I increase the pressure, in previous video also I explained that part. When we increase the pressure, our requirement of latent heat for conversion from liquid to vapor get reduced. When 1 atmospheric pressure is there, our requirement of latent heat is from this point to this much amount of heat is required. If I increase the pressure, so I observe that liquid point is here, saturated liquid, vapor point is here. Now I have to supply this much amount of heat only, latent heat. That means requirement of supply of latent heat for conversion liquid to steam is reduced. And at this point, maybe our boiling temperature of water is different. Suppose this is T1. So technically, if you are talking, water is boiled at 100 degrees centigrade. Along with, you have to specify at atmospheric pressure. But if you rise the pressure, then your temperature of boiling will increase. So if you boil any pure substance under higher pressure, your boiling temperature is increased. That means now you can rise your water to higher than 100 degrees centigrade if pressure is more. Otherwise, at atmospheric pressure, you never increase boiling temperature. It will boil at 100 degrees centigrade. But if you want higher temperature water, suppose 110 degrees centigrade water, liquid form, then you have to maintain that water under higher pressure. So we can obtain 110 degrees centigrade water. But for that, requirement is our pressure should be higher. Now suppose I am decreasing the pressure. If I reduce the pressure below the atmosphere, we are saying it is a vacuum, correct? Negative pressure. So suppose I decrease the pressure. So I am using any vacuum pump and I am decreasing the pressure, and then suppose this is pressure line, and this pressure line, suppose P is equals to suppose half atmosphere, 0.5 atmosphere. As I decrease the pressure, I found that the total heat supplied, that is latent heat supplied for phase change, for converting saturated liquid to saturated vapor, the total amount is increased. So whenever we increase pressure, our boiling temperature will increase. Whenever we decrease the pressure, our boiling temperature is decreased. So T is equals to, suppose now 70 degrees centigrade. Suppose for the example, T1 is suppose 210 degrees centigrade and T2 is 70. That means when we reduce the pressure, we can boil water at lower temperature. Boiling temperature will reduce. Now the second point. We are considering this line only. Now we are talking about the properties. This is saturated liquid line, saturated liquid curve. This is saturated vapor curve. Now at this point, this is specific volume, correct? Specific volume. Sorry, this is specific entropy. TS diagram is there, so it is specific entropy. Specific entropy at this point. Now at this point, it is completely in liquid form. So we can say specific entropy of fluid. Liquid, but it is given as a suffix F. When we are plotting specific entropy at this point, here pure substance or that water is completely in vapor form. So we are saying specific enthalpy of gas. So specific enthalpy of vapor, it is noted in a standard form, that is G, specific enthalpy of gas. Sorry, specific entropy of gas. Now if I am checking at this point, so as I get entropy, specific entropy of fluid, so similarly at this point I observe that if I am calculating enthalpy, so here I get enthalpy, specific enthalpy of fluid. If I am checking here what is the specific volume, so I can write it as specific volume of fluid. At this point, I can write specific enthalpy of gas, specific volume of gas. So whenever there is F, suffix F, so it is for fluid, that means it is for liquid form. Whenever there is suffix G, then it is for gas, that means a vapor form. Now at this point it is a fluid, at this point it is a gas, but in between this there is a mixture of liquid and vapor. Not completely liquid, not completely vapor. So from this to this there is a mixture of liquid and vapor, and corresponding properties are denoted as Enthalpy, it is said that enthalpy of fluid and gas. So it is a mixture of fluid and gas. So whatever be the property in between these two saturated condition curves, suppose it is enthalpy, so it is enthalpy of fluid and gas. If it is talking about entropy, so it is entropy of fluid and gas. Now in this, there is a different proportion of vapor and liquid. So accordingly, we can find out what is the dryness fraction. So this is the X. Constant. So dryness fraction lines X is equals to constant. So here X may be 0.4, 0.6, 0.8, anything. But these are the constant dryness fraction line. So now here we come to know that when I am talking about this point 1 and this point 2, I am supplying heat. So when our substance reach to state 1.1, then its enthalpy will be HF. When I supply continue heat and our substance reach to point 2, then our enthalpy will be Hg. When it is in between 1 and 2, then it is written as HFG. Now suppose I don't know the enthalpy, the correct position. Suppose anywhere, suppose this is the position of our state. Suppose this is point 3. At point 3, if I am interested to find out the enthalpy, so enthalpy at this point 3 will be, at least we have to supply this much HF, so HF will be there. After that, we are not reaching to Hg, we are in between that, and here there will be certain dryness fraction. It is not completely liquid, not completely vapor. So here at this point there will be a certain dryness fraction. Suppose that dryness fraction is X, so it is plus X. That means this much dry steam is there. Now this is belongs to 3 point. So at 3 point, what is the enthalpy? H is the enthalpy at 3 point. For this calculation is HF plus this much enthalpy. For this much enthalpy, I must know what is the dryness fraction at this point. Dryness fraction is X. What is the enthalpy from this to this? This is wet vapors, wet steam. So for this portion, we always written as HFG. Same way, if it is entropy, specific entropy, so for point 3, entropy of fluid plus dryness fraction multiplied by entropy of fluid and gas, because it is a wet. Similarly, specific volume, so volume, specific volume of fluid plus dryness fraction plus specific volume of fluid and gas. But in fluid specific volume, it is observed that there is never mention a fluid and gas. In steam table, there is no such column, VFG. So for this SFG, HFG, that VFG, we can write this much HF up to this HFG, then we reach to HG. So HG is always equals to HF plus HFG. Sg is always equals to Sf plus Sfg. Similarly, specific volume volume Vg is equal to V of fluid plus P of fluid and gas. From this relation, we can calculate how much is the HFG. HFG will be Hg minus Hf. For this Sfg, if I am shifting this, so it become Sg minus Sf. And in the same way, if I am interested to find out Vfg, so it will be Vg minus Vf. So in steam table, the columns are there for HF, Hg, Hfg. So there is no issue. Either you can take a value for or HFG, otherwise you can minus Hg minus Hf, so we get the HFG. Similarly, for entropy, there is a column of Sf, then Sg as well as Sfg. But for specific volume, there is only two columns, Vg and Vf. So whenever it is a wet steam, we require a Vfg. So if there is no column in steam table for Vfg, so we rearrange this, and whenever there is a requirement of Vfg, so we simply take a value of Vg minus Vf. So these are the formulas we require. So let's see one numerical. So these are all points will be clear. Okay. Numerical statement is find the enthalpy and entropy of a steam when enthalpy and entropy
Sir, above question is not visible.
of a steam when the pressure is 2 megapascal and specific volume is 0.09 meter cube per kg. So there is one numerical to find the enthalpy and entropy of a steam when the pressure is 2 megapascal and specific volume is 0.09 meter cube per
Sir,
kg.
question is not
Now
visible.
it is not said specific enthalpy or specific entropy. It is the total enthalpy. When we are talking about a total enthalpy, so it is denoted by capital H. And capital H total enthalpy means total mass multiplied by specific enthalpy. Mass having a unit kg, specific enthalpy having a unit kilojoule per kg. So total enthalpy is always measured in kilojoule. When we are talking about a total entropy, capital S, so it is nothing but a mass of that substance, pure substance, multiplied by specific entropy. Specific entropy, that is per unit mass. It is denoted by small s. Mass is always measured in kg and specific entropy is measured in kilojoule per kg Kelvin. So kg get cancelled. So we get an entropy, total entropy kilojoule per Kelvin. So remember, there is either total enthalpy or entropy or specific enthalpy and entropy. Now here there is no data related to mass. In this case, we have to assume mass is equals to 1 kg. So if it is a per unit mass 1 kg, that means we are calculating small h, specific enthalpy and specific entropy, because it is per unit mass. Specific entropy per unit mass. So if mass is not given, so we will assume mass is 1. So accordingly we can calculate the enthalpy. So in actual they are asking for specific enthalpy. Otherwise you assume mass is equal to 1 kg and find out the total enthalpy and entropy when mass is 1 kg is assumed. If you don't want to assume the mass, then directly find out specific enthalpy and specific entropy. So for this problem, we are going to calculate specific enthalpy because mass is not given and specific entropy. Now, TS diagram, specific entropy and temperature. We know that we get this such kind of bell-shaped curve where this is critical point, saturated liquid line, saturated vapor line. Here the pressure, constant pressure line, when it reach to saturation liquid, then after phase change take place at constant temperature, so horizontal line. Then after again there will be rise in temperature. This pressure they given P is equals to 2 megapascal. And they given a specific volume. Specific volume P is given 2 megapascal and specific volume it is 0.09 meter cube per kg. But here we don't know this specific volume belongs to saturated liquid or saturated vapor or in between this. If this specific volume 0.09, suppose it is come here, so that means the steam is wet steam. If it is a wet steam, that means it having some particular dryness fraction. If it is here, then dryness fraction is 0. Here dryness fraction is 1, but in between this there will be some dryness fraction value. So this is constant pressure line. Now in steam table, most of the steam table, the pressures are given in bar. But if your data is given in megapascal, kilopascal, so we have to convert into bar. How to convert it? 1 megapascal is equals to 1 multiplied by 10 raised to power 6 pascal. And 1 bar is equals to 1 into 10 raised to power 5 pascal. So we can find that megapascal upon bar, if I am simplifying this, it remains only 10. That means 1 megapascal is always equals to 10 bar. This is the relation. We have 2 megapascal, so pressure will be 20 bar. So pressure is given 20 bar and specific volume is given 0.09. Now let us see how to calculate the required enthalpy and entropy. This is steam table, and most commonly it is used by university. It is given by R.S. Kurmi. So it is suggested to have this steam table. In this complete steam table, many things are given. Just like definitions, what is steam, formation of steam, what is the property of steam, that is specific volume of steam, specific enthalpy of steam. Steam tables, these are the properties, even though formulas also. This is the enthalpy of mass m, and this is the formula HF plus X into HFG. That's why it is belongs to wet steam. So formula will be there. All the lines on the graph, Mollier diagram, which are the lines, the dryness, fraction, constant, specific volume lines are. All lines descriptions are given. Now we will move on to table 1, tabulated table. So temperature is given in degree centigrade in this table. If in numerical it is given in Kelvin, so convert into degree centigrade. So this is saturated water and steam table, but on the basis of temperature. So first column is temperature. And what are the different values? So for corresponding temperature, saturated temperature, what is the absolute pressure? Specific volume. So here we can observe that specific volume is given only for Vf and Vg, not for Vfg. Specific enthalpy unit is kilojoule per kg for HF, HFG and Hg. Similarly, specific entropy for water, SF, SFG and SG. So this is saturated temperature. In our numerical, it is given a pressure 2 megapascal. So we will refer a second table which is given the values on pressure. So first column is absolute pressure in bar. So steam table having a pressure unit in bar. So we have to convert megapascal into bar. What are the different properties? So according to this, whatever be the respective pressure, corresponding saturation temperature will be there. Specific volume, Vf, Vg, enthalpy, HF, HFG and Hg, entropy, SF, SFG and SG. Now, our pressure numerical given the 20 bars, correct? We convert into bars, so we observe that the pressure become 20 bars. So we will go for 20 bar pressure. It is 2, then 5, 12.5. Now here. So this is 20 bar pressure, correct? First column belongs to temperature. So at 20 bar pressure, what is the boiling temperature or saturation temperature? It is 212.4. That means this is the constant temperature where phase change takes place. So as earlier I said, at 1 atmospheric pressure, our boiling temperature of water is 100 degrees centigrade. But 20 bar, it is 212.4 degrees centigrade is the boiling temperature. This is the first volume value, that is Vf, 0.001177. This second Vg, 0.09955. Next is HF 908.5, then HFG 1888.7, HG 2797.2, then SF entropy 2.447, SFG 3.890 and SG 6.337. Again a pressure line, pressure column is there. So we have to use this scheme table and find out these all values corresponding to our given data. In our given data, it is given a pressure, so we use this pressure table and corresponding value we will note. Specific enthalpy, so it is kilojoule per kg. HFG having a value 1888.7 kilojoule per kg, and HG it is 2797.2 kilojoule per kg. Now corresponding entropy values. So SF is 2.447 kilojoule per kg Kelvin. SFG is 3.890 kilojoule per kg Kelvin, and the last is SG is 6.337 kilojoule per kg Kelvin. So from steam table we come to know what are the properties of our required steam as per the given data. So at 20 bar, what are the different properties? So we note down all these properties. Now we don't know whether that steam is dry, saturated vapor, saturated liquid, or it is in wet zone. So we have to first find out what is the X dryness fraction. If it is 0, then we can say it is saturated liquid. If it is equals to 1, saturated vapor. But if X value lies between 0 to 1, that means it is a wet steam. So we have to find out. We know all this given data from steam table. So if I am using enthalpy of steam is not given in numerical. Entropy of steam is not given, but specific volume of steam is given. So specific volume of this given steam is equals to, how to calculate? So specific volume is nothing but specific volume of fluid plus X, that is dryness fraction, into specific volume of fluid and gas. But there is no column, no data for fluid and gas specific volume. So we will rearrange specific volume of fluid plus X into specific volume of gas minus specific volume of fluid. So given specific volume is 0.09. Vf corresponding to given pressure is 0.001177 plus X dryness fraction we don't know. Vg is 0.09955 minus 0.001177. So only unknown is X. If I simplify this, so I come to know what is the dryness fraction. If this X value is 0, that means our steam, that is our substance, is a liquid form, saturated liquid. If it is equals to 1, then vapor, saturated vapor. After calculating, we come to know that X is 0.9029. That means it is lying in between 0 and 1. That means our steam is wet. Now, the final answer, enthalpy. So, enthalpy H of this steam is HF as it is a wet stream, so X into HFG. You may use Hg minus Hf also, but HFG value already there, so we will take that. So HF 908.5 plus X value is given now. We calculated, so it is 0.9029 multiplied by HFG 188.7. So when we calculate this, we come to know that the specific enthalpy of this steel is 2613.81 kilojoule per kg. This is our first answer. Now in the same manner, we can calculate entropy. So entropy will be, specific entropy will be entropy of fluid plus X dryness fraction into entropy of fluid and gas. Entropy of fluid, it is given 2.447. 2.447 plus X is 0.9029 multiplied by SFG. SFG is 3.890. 3.890. So when I calculate, so specific enthalpy of this given steam is 5.9593. 5.9593 kilojoule per kg Kelvin. This is the specific enthalpy. Now imagine if they given a mass of steam, suppose 2.5. So once we come to know what is the specific enthalpy, so total enthalpy will be multiplied by 2.5, that is the mass. Here total entropy will be multiplied by 2.5. So remember, direct total enthalpy is not possible. We have the all formulas for specific volume, specific enthalpy, specific entropy. So we have to calculate first specific values and then calculate the total enthalpy or entropy.